So, hello everyone, I am Abhishek Jedli, and today I'll be walking you through the formal proof that both the set of strings of prime length and set of strings of non-prime length over a single letter alphabet are not regular languages. And we'll use the pumping lemma theorem as the main tool and see why finite automata simply can't handle the complexity of primes. And this topic is not just a theoretical curiosity, and it shows where the power and limits of regular languages lie. So that's my topic, non-regularity of primes and non-prime languages. And we'll be solving it through the pumping lemma. So let's just proceed. So first, I'll give you a brief of what's a regular language. Languages that can be recognized by finite automata, either DFA or an NFA, is called a regular language. So DFA is basically a deterministic finite automata, and NFA is a non-deterministic finite automata. And we have two types of languages. Basically, we have a finite language and an infinite language. All the finite languages are always regular languages. And for the infinite languages, we cannot certainly say whether that language is a regular or not regular. So for that particular case, for an infinite language, for proving that a language is either regular or non-regular, we have this theorem called as pumping lemma. In this, we define a string in which we take a string of the language and we decompose it into three parts of x, y, and z. And we raise the y to the power of I, and where I is known as the pumping limit, or till which we can pump the value of y. We take y as a substring of the entire string that we have taken into consideration. So I'll be explaining you the pumping lemma first, and I'll then guide you through these two questions basically. That is languages to analyze over here. As you can see, one is whether the language L, that L belongs to A, where A to the power of n, where n is prime, and A to the power of n, where n is not a prime. So we'll be analyzing these two questions as in particular in these two questions. So let's get started. So pumping lemma. If L is an infinite language, there exists some positive integer n, where n is the pumping length, such that any string W is a string that belongs to the language, and that has a length greater than or equal to n. So, that is mod of W. This is defined as the length of the string that we have chosen. So mod of W should be greater than the pumping length, where W can be divided into three parts. As I said, the string that we choose is divided into three parts. That is X, Y, and Z, and it should satisfy this condition. Uh, the three conditions that it should satisfy is that for each I greater than or equal to 0, X, Y to the power of I, and Z should belong to the language. Mod of y should be greater than 0, and mod of x should be less than or equal to the pumping length. So I told you right now, we'll in the language over here, we'll take a substring, and in that string, we'll just uh, make it in the form of x, y to the power of I and z, and we will pump the alphabet y over here with the different values of I ranging from uh, 0 to the pumping length. So whether a pumping lemma is a positive test or a negative test, I have just drawn a basic flow chart over here that defines that. So what pumping lemma actually does is uh, it accepts a language, and when we follow the procedure of pumping lemma, if the language passes that test, It's undecidable whether the language is regular or not. And if that particular language fails the pumping lemma test, we can surely say that that particular language is not regular. So when is the case of confirmation comes, that's when our language fails the steps that we follow in pumping lemma, or at the end of pumping lemma we find a I value such that x, y to the power of I and z does not belong to L. Only that time the pumping lemma fails, and hence it is decidable that that particular language is not regular. So we can conclude something with the help of pumping lemma only when our test fails. Hence, it is a negative test. And I have shown a pictorial representation of same flow chart over here as well. And I just told you, right, that there are two types of language, finite and infinite. And finite language are always regular, and infinite language, we cannot decide whether it's regular or not. So now we know what pumping lemma is. Let's go further. Over here, in pumping lemma, these are the key conditions that we already discussed, right? So these are some steps that we should follow in order to get pumping lemma, what you call, in order to prove a language is regular or not using pumping lemma, we should follow these particular steps. So first step is that we assume that the language is regular or not. Then we take a string from the L that we have defined, and we define two things. One is the Y value and one is the pumping length. And we take these two constraints and follow the remaining procedure where we find a generalized expression of x, y to the power of I and z. And then if we get a negative test, or if we fail at some condition or at some value of I, only then we can conclude the language is regular or not regular. So over here, let's check that for this language, this particular language, that a to the power of n, where n is prime, is regular or not. So first of all, this we cannot design a DFA for this language. And why is so? I'll just explain. So first of all, what is a DFA and what are the limitations of us drawing a DFA? If we draw a normal DFA for a to the power of n, we'll see that we have a normal starting state. We have a loop that after uh, a certain number of inputs, we have repetition in the cycle of inputs. So the fundamental limitation is that any DFA must enter a cycle after processing a sufficiently long inputs. And this creates a regular pattern where if a DFA has n states, it must repeat states after processing at most n symbols. So this recursiveness or this cycle forces an acceptance or forces an event where a particular string will get accepted. And this cycle is also proved in pumping lemma, and that cycle in pumping lemma follows a principle called as pigeonhole principle. We'll see that in further slides. But right now, for this particular language, we can see that since it's theoretically impossible that DFA cannot be formed, because DFA has these limitations that there must be a cycle. But what we see here, since a to the power of p, where p is a prime number, uh, we cannot find any regular interval or regular patterns that follow the string. Like over here, let's take p to be 2, 3, 5, and 7. Okay, so over here we have a constraint that p should be less than equal to 10. For that particular constraint, we can draw a DFA. of 11 states from Q0 to Q10, as I have drawn it over here. And with the input of A on each string, on each step, we can have one, two, three, and four final states. That is Q2 as the acceptance state, Q3, Q5, Q7. As 2, 3, 5, 7 are prime numbers that are less than 10. So with a constraint in DFA, we can design this string. But you know the differences between the primes. That is, we have a difference of one between two and three. We have a difference of two between five and three, and we have irregular intervals of difference between each prime. So we won't have any particular cycle that will help us to generalize the DFA. We can also consider an NFA as well. I'll just focus on that. We cannot draw a DFA over here because if we draw a DFA for a language, then we can prove it as a regular language. So this is the foundation that we cannot draw a DFA for this particular language. Okay. So let's get into what I refer to as pigeonhole principle, right? So the pigeonhole principle forms the foundation of pumping lemma, appearing in a critical but often implicit way in proving that this particular language L is a regular language or not. So have you ever heard of the pigeonhole principle? It states that if you have more pigeons than holes, like suppose if you have uh, two pigeons and if you have one hole, then two pigeons should share a hole. That means for DFS processing a string longer than the number of states, uh, it forces state repetition. And this repetition leads to the split uh, that happens over here, right? We have a decomposition of this string, that is a to the power p, into x, y, and z. So this repetition itself forces the decomposition of the string into x, y, and z. And if this what you call repetition is not there, then we cannot pump the y to break the primality, and hence this principle silently powers the entire proof of pumping lemma. So in order to have a to the power p as a regular language, we need to have some pigeonhole principle that is being applied, some cycle of repetition that should be there in the DFA that we can try to design. But of course, we are not able to design a DFA. That's I just explained that. So let's go to the next slide. And over here, I have just written the entire proof of how we prove that this is not a regular language. So the step one is that we have to assume that this particular language is regular. Step two is that we have to build the sample space of the entire what you call the entire string that belongs to language L. That is a to the power 2, a to the power of 3, a to the power of 5, and a to the power 7. All of these, and so on, like a to the power 11, a to the power of 13, these belong to the language L. Now we pick a generalized string W where W is equal to X, Y, Z, and that belongs to L. I had already told you that mod of W should be greater than equal to the pumping length, right? Here, M is the pumping length, and M is a really large number. And P is a prime number, as we have taken, and we have assumed that P should be greater than the pumping length. We have already seen that this has to be taken under consideration. This has to be followed in order for us to follow the procedure of pumping length. So the next step is to decompose a to the power of p into x, y, and z, right? Now, according to the pumping lemma, any sufficiently long string in L must be decomposable into these parts. So over here, we just were to take y's value as a to the power of k, and where k's range is between 1 and m included. So by this step, we can confirmly say that a to the power of p, that is the original string, can be represented into x, y, and z, and where y is equal to a to the power of k. A to the power of k is just a part of the entire substring w that we have taken. It is not the entire string, it's the part of the string that we have taken. And we are going to pump this y in order to try to find the I value that uh, with help of which that x, y to the power of I and z will not belong to L, and there the negative test prevails, and hence we can prove that this language is not regular. That is going to be our step-by-step theoretical approach. So what happens over here in step 5, we try to pump y. So we have considered I is equal to p plus 1. Now, why particularly p plus 1? I'll just get to that in a moment. And let's just try to derive a generalized string that is x, y to the power of I and z, because we have to pump I, right? So I need a generalized string where it contains a, p, and k, and I where, in a particular string itself instead of x, y, and z, because x, y, and z I have assumed, and I need it in the form of a as that is the single alphabet that I have been provided with. That is the core alphabet that makes the entire string. That's the non-terminal symbol, basically. So over here, a to the power of p and a to the power of k. We have taken y as a to the power of k, and we just split y to the power of I in y to the power of I minus 1 into y. This is basic arithmetic. And x to the x, y, z, we have already assumed it to be a to the power of p. So we conclude the generalized expression of x, y to the power of I, z to be a to the power of p plus I minus 1 k. Now, why p plus 1? Why did I take p plus 1 over here is, so first let's try to substitute a value that is not equal to p plus 1. So if we substitute I is equal to 1 for this, we get the original string that is AP, right? And that obviously belongs to the language. Now let's try substituting I is equal to 2. For x, y to the power of 2, z, x, y, it makes the generalized string into the form of a, p plus k. Now over here, p plus k is the power of a. Hence, we need to choose p and k such that p plus k is a prime number. And if we can choose p value and k value such that p plus k belongs to the set of prime numbers, then we can confirmly say that a to the power of p plus k belongs to L. Hence, this is a positive test, and hence we cannot decide whether this language is a regular language or a irregular language, right? So let's go to the next slide over here. I took the value of p as 2 and k as 1. These are the constraints that have to be followed all along the proof that, of course, a prime number always has to be greater than or equal to 2. And we already assumed k's value that should be in the range of 1 to m. So if we add p and k, we get 3. So that makes it a to the power of 3, that is a. And this already belongs to L. Similarly, if we take I is equal to 3, we get for values of P is equal to 3 and K is equal to 1, we get this string as a to the power of 5, and that also belongs to L. So as we discussed earlier, if pumping lemma passes the test, we are not able to decide. So we need a string with help of which this test fails, and hence we are able to decide whether this language is regular or not. If it fails, we can conclude with assurance that this language is not a regular language. So let's take p plus 1 as the value of I and prove that why p plus 1 works. So the key observations that we have taken, that p is a prime, of course, p should be greater than equal to 2. and k's value, it ranges between 1 to m. That's also certain, right? So if we take the value of p plus 1 and we put it into the generalized string, we get a to the power of p 1 plus k. This is the value of the generalized string that we get after substituting I is equal to p plus 1, right? Over here, when 1 plus k is greater than or equal to 2, how did we arrive at this conclusion? Let me just guide you through it. We know that k's value is greater than or equal to 1. Over here, I have already written it as k is between 1 to m. M is the pumping length, if you forgot. M is the pumping length over here, and k is greater than or equal to 1. We'll add 1 to both the sides of the inequality, and hence we'll get 1 plus k that is greater than or equal to. This means 1 plus k is an integer that's greater than 1. As over here with this equality, we can see that uh, range of k plus 1 starts from 2. That means it obviously does not include. That means k is something greater than 1, and we had already assumed. So mathematically speaking, p is a prime number, and this particular thing, that is 1 plus k, is greater than. Since both the factors are integers greater than 1, hence p into 1 plus k is a composite number. And hence we can say that the power of a is a composite number and not a prime in this case. And hence over here we can conclude that a to the power of p 1 plus k does not belong to n. And hence the language a to the power of n, where n is a prime, is not a regular language. Over here, I have shown an example as well, where if we take I is equal to p plus 1, it does not follow uh, this particular language case. For example, p is equal to 5, then p is a prime number, and k is equal to 3. That means y is equal to a to the power of 3. We had taken y is equal to a to the power of k, right? So let me just put the values of p and k over here, and we get the answer as 20. And 20 is obviously not a prime, right? It's a composite number. Because what are prime numbers? Prime numbers are basically the numbers who are who have a factor of 1 and the number itself. Like 3 has a factor of 1 and 3, and five's factor is 1 and 5 itself, right? So therefore, prime number is a number which has a factor of itself and 1. And over here we have 20 as the answer, which is a composite number. 20 has factors of 1, 2, 5, 4, 20, 10. Yeah. So that makes it that makes it a composite. And hence we can prove that uh, this string is not a regular language. So yeah, we'll have another proof of this same thing with respect to the size of W. That means the length of W. Now we knew that x, y to y, z is equal to a to the power of p, right? Over here, what does this mean? If you have a string, suppose a to the power of 2, a to the power of 3, what is the length of that particular string? It's nothing but the power of a, right? Uh, like a to the power of 3, we have 3 a's, hence the length is 3. A to the power of 5, we have 5 a's, hence the length is 5. So over here, xyz has a to the power of p, hence the length of xyz should be p. That same thing I have written over here. So if I generalize the expression of a, so of x, y to the power of I, z, and I put the value of I is equal to p plus 1, we'll have this generalized equation derived, that is p 1 plus mod of y, right? So this mod of y should always be greater than equal to 0, right? This thing cannot be equal to 0 because we took y as a to the power of k, and we know that k is always greater than 1. It's not equal to 0, right? If k was equal to 0, then y's mod could have been 0. But since k is greater than or equal to 1, y's mod can never be 0. That means 1 plus a something. That something is a positive value. And hence, over here, we can see that again it follows the principle that the multiplication of p into 1 plus mod of y is not a prime, as it has factor p and 1 plus mod y, right? It has two factors. And hence it's a composite number and it's not a prime number. And hence by this proof also we can prove that a to the power n is where n is a prime is not a regular language. So uh, let's get into our second question. Yeah, so over here I have just defined all the things that we have discussed, that why we took a to the power of p as x, y, z. Why did we take I is equal to p plus 1? Why did we take y is equal to a to the power of k? And why did we take p's value, why p 1 plus k is composite? Yeah, we already discussed all of this. So this is a question where L is equal to a to the power of n, and n is not a prime. So we have to prove whether this language is regular or not. So in regular languages, we know that regular languages are closed under some particular rules. Regular languages are closed under intersection, they are closed under addition, concatenation, union, and also regular languages are closed under complement. So by complement, I mean that if a language L is a regular language, then its complement L prime or L bar is should also be a regular language. Like if L is a regular language, L bar also has to be a regular language. It's simple as that. Because if we were to draw a DFA of a regular language, then it would have some final states and some non-final states. And if we interchange the final states to non-final states and non-final states to final states, then we would get the DFA of L bar or L prime. That is the complement of L. So we have already learned that, and hence we have seen that when L was equal to a to the power of n, where n is a prime number, we found that it is not a regular language, right? So hence, by the rule of complementation, we can clearly state that L or L prime also would not be a regular language. So means that over here, L prime is defined as a to the power of n, where n is a prime number, because L is defined as where a to the power of n is not a prime, right? So L prime would be where n is a prime. So we just now prove that when n is a prime, we cannot design a DFA. And also by pumping lemma, we saw that for I is equal to p plus 1, it was not a regular language. Hence, by complementation, we can also say that this language is also not regular language. So these are the two questions that we learned today. And here is the what you call word type format of both the answers of both the answers of both the questions. And yeah, the theoretical foundations that we also learned was pigeonhole principle. I just explained you what pigeonhole principle was, and limitation of finite automata. That also we discussed that why DFA cannot be drawn of e to the power of n, where n is prime. And conclusion, some things that we learned over here, that these the pumping lemma is a very elegant use of language complement, and these techniques are fundamental in formal language theory and have connections to the conceptual complexity, number theory, and limits of finite computation. So we learn these things in theory of computation, and hence I would like to just conclude my presentation. And I hope I was able to explain both the questions precisely and perfectly. Thank you so much.